Hey guys, welcome to my YouTube channel. So today we're gonna look at another interesting system design problem. So we're gonna try to design the financial dashboard, or more like a trading view dashboard. So this question is often asked on the interviews at the trading companies. So I think it's pretty cool that we can look at this problem and try to design the architecture for of the solution. So without further ado, let's continue and go to our drawing board. All right, so essentially what we are going to try to build is the trading view. So you know that there is a tool called trading view, and it allows you to kind of have the multiple finance charts, for instance, stocks or any other finance assets on the screen. So I can actually open the trading view and show you how it works. So essentially you can have multiple layouts. So for instance, you can create a 6-column layout, and each layout can have its financial assets. So for instance, here NVIDIA, Apple, PayPal, and essentially we can resize every window. And see, every window is resizable. We can also do some fancy things like synchronization. So for instance, we can say that we want to synchronize all the charts by the interval. And if we change the interval to 1 hour, every chart is synchronized by this 1 hour interval. So what we can also do is synchronize it by also different things, for instance, by the symbol. So if I choose the apple here, all the charts updated with an apple. So, and our main challenge in this problem is to actually design the layout that would support this type of resizing, as well as how do we handle the large set of data that comes into the chart, and how do we reuse this data across the charts. So yeah, I think it's pretty interesting to look at this. So yeah, let's go back to our drawing board and we can actually understand how we approach this. So I already prepared some simple interview plan, and as a first step, we're going to look at the requirements and the mockup. The second one is the layout design. So we're going to try to understand how to design this layout. And another one is the data model. So how do we represent the finance data, and how do we store this data in application state? Also, we need to understand how do we communicate with the backend API, and what's the best interface, what's the best protocol to connect to the backend. Another one is the data flow, how the data flows through the components, how do we synchronize the charts, and how do we support the multi-monitor. So for instance, you have the main monitor and you want to extend your application to the second monitor, so by opening, for instance, at the top, and how do we do the synchronization between these two tabs. And before we jump into the drawing, I want to first understand the requirements for this problem and kind of have the very quick mockup. So what are the product requirements for the financial dashboard like that? So I think the first one is each dashboard should support multiple resizable charts. So we can place as many charts as we want. The user can configure basically all layout types as long as it's a grid. And the data may come from different data sources. So this means that you may have all like different APIs. So these APIs may be some legacy APIs, some new APIs. But one thing that we want to make sure is that all these APIs actually return the same data. So data type, this means that data interface is unified across these APIs. So another thing is, if we want to think about extensibility of our application, so that each chart technically can have a different data model. So for instance, table may have its own data model, or the pie chart or bar chart, and so on. However, the model that comes from the server is always generic. So this means that each chart will know how to transform this data, so to display it. And yeah, so we can also have some synchronization parameters that we can use, for instance, asset ID and time frame. So if we select the asset ID on single chart, and if we selected the synchronization mode, then all the charts should be updated with this asset ID. It's more like a bonus point in this design. I think it's not the most interesting part, but anyway, good to have. So from the non-product requirements, I would say that the network performance is something that we want to focus on, because essentially we have so much data coming into the browser, and it would be good to understand how can we optimize the data loading so we don't load too much stuff, so we utilize the browser cache, and so on. So another thing is rendering stability. So when we change the parameters of the data, can we still display some partial charts? So for instance, you change the time frame from day to the 1 hour. So can we somehow downscale the data so we can display the chart in 1 hour time frame without actually requesting the data yet? And another thing is the legacy API. So we want to somehow have a unified interface that will be working across different APIs. So for instance, you're a developer, you have 5 APIs that follow the same generified response model. So we want to utilize all this legacy API as a single method. All right, so it's too early for canvas design. And since we already mentioned all the products and the non-product requirements, we can move to our dashboard. And in order to save some time, I already prepared this product requirements and the mockup. So essentially, it's the same thing that you saw on the slides. All right, so in terms of the mockup, to save also some time, I already prepared the mockup for us. So that's the mockup. So it's essentially going to be the column design where we can place multiple charts. And we are not limited to this design. So essentially the chart can take any available space and the user can configure the canvas the way the user likes. All right, so what's our next step? I think since we've mentioned all the requirements now, we can now move forward to the layout design. So I'll create a section on my board and I'll call it layout design. All right, so what do we do? What do we want to do with our layout design? So as we already mentioned, our layout design is essentially kind of a grid. So we want to have a grid system similar to the CSS grid, or I would say. So our first bullet point will be use grid system. And then our second point will be that user can adjust grid layout. So it can be, for instance, 8x8 or 6x12. And so on. This is configurable by the user on the user side. So one thing that we can think about is, so since it's a grid system, so what is the analogy we have in the front-end development? So essentially CSS Grid is something that kind of matches our parameters. And in the requirements section, we mentioned that, so usually we don't expect the users with Internet Explorer to work on a trading desk. So we actually assume that the user will have the support for the most modern browsers, so which is good. So we are not very limited by the technology that we can use. The CSS Grid is super convenient in this case. So CSS Grid will be super useful comparing to Flexbox, because it's a natural grid that is provided by the CSS standard. So, and another thing is, okay, we have a CSS grid system, but the main challenge will be how do we implement a drag and drop? So how do we place the charts on our canvas? So yeah, and for that, I'm going to introduce the concept called like sandwich design. So essentially and I'll explain it just in a few seconds. So we're going to implement a drag and drop and use overflow grid mode. So essentially CSS Grid allows to place the same multiple items in the same grid section. And I'll explain that just in a few seconds. So I think we have all the requirements for layout design. Let's go back to the slide so I can explain the concept in a better way. All right. So we'll start with the empty container. So this will be our container where we'll place all our content. And what we want to achieve is kind of split this container into these sections. So we'll have our columns and then we'll have our rows. So this is how it would look like if, for instance, so this will be row 0, this row 2, this is column 0, and then column 4. And I want to place my chart, for instance, on this rectangle like that. And how can I achieve this relatively easy with the CSS standard? And the answer is CSS Grid. So essentially we can assign our container with the following configuration. So our container will have the display grid, and then the green displayed columns and rows will be configured by the user settings. So this user setting number will tell us how many columns and rows will have our layout will have. And here I say one fraction, but it's so it's not really one fraction because the user can resize every column. But for now, we assume that every column will have the same width and the height. So it's very easy to adjust. Okay, so this will create the grid with the container like that. So now I want to place my chart on the grid. When I place that, so I can assign this container the following style: green column 1 free and green row 1 free. This essentially will span my chart container on this section. So this is basically how we're gonna place our charts. So every time we place the charts, we place the chart container onto the grid, we're gonna span this container across our grid system. And the way it's gonna work is every cell in our grid will be a small container that will listen to the drag and drop events. So essentially, when we move our rectangle, it will we will fire the drag and drop events. So, and whenever we drop the container onto the grid, this small cell will try to call the drag and drop event that will tell us where our mouse pointer was. So in this case, our mouse pointer was on the row in column 0, and we can assign the data attributes to this cell to understand where we drop the container. And when we drop it here, we can assume, for instance, that each chart will take by default 2 columns and 2 rows. So we will set the calculation. So we will take this rectangle, so it's initially dropped here, and then we use the CSS Grid to span it like that. So this is the way how it's going to work. And I'll explain, and this is called the actually sandwich design, because you're using 3-layer system, and I can demonstrate it here. So if we open this example, so see, this is our first container. And then we have another, the second container that, not the second container, but a second set of small containers that listens to the drag and drop event. And then we put our chart box on top of the of these 4 containers, 1, 2, 5, 6. And this is done very simple. I can go to the source code now and see this is our basically grid, and we have 12 boxes, and then we put the chart as the last box in the container. And this chart is just assigned with the grid column 1 free and grid row 1 free. And we can actually build this sandwich as much as we want, because the CSS spec allows us to do that. Okay, I think we kind of understood the idea what we're doing here, and we can go back to the to our Draw.io. Okay, so this is how our design will look like. So we can now drop it here. So this is our container, and as the first step, we'll create the so we'll call it layer 1. So let's call it layer 1 grid container. All right, so this is the CSS grid that we created. The next step is to create a cell grid. So how do we create a cell grid? So it's essentially our cell, and here I try to draw the pointer, and this is the container that we want to place. So when we point at the sum cell, so essentially what's going to happen is the cell will pass the events to the parent container, because all the events in the browser, they bubble. So here we create here as our grid container, and we can place on top of the grid container the handler that will handle all our events that are coming from the grid. So this thing will allow us. To handle to register just a single handler on the grid container and handle all the events for the whole grid. So we could opt into the different things. So we can technically assign the handler to each cell, but this will not be memory and performance efficient. So because you will have to have, for instance, you have a grid 8x8, this means 64 handlers registered on the event loop. So this will not be very well performance optimized. That's why we want to use the event bubbling here. So here I place the text, the event bubbles top from the main grid, so we can handle it on the root level. So, and how do we understand which cell we actually are referring to? So we can use the data attributes. So each cell will have 2 data attributes. So we can say data column equals to 0 and data row. So this way we can understand exactly where the pointer drops the container. And we use a standard drag and drop API, which have 4 events like drag start, drag end, drag move, and so on. So we don't want to dive into the drag events here, but when we do the drag end, so this event gives us the container where the event stopped. And essentially when the mouse points at this rectangle, we'll get the target of this rectangle, so of the cell, and we can get the data column and data row, so we can assign our chart content the proper CSS style. So let's quickly write down what I think here. So first thing, each cell will represent a droppable container. This is our first point. Second point, we set the data attributes to each cell. The third one is when the mouse pointer targets the target cell, when mouse pointer targets the cell, we receive the container. When the mouse dropped, we use drop end event to get the final element where we need to place the chart. All right, so this is the basic idea. And once we place the chart on the screen, so here's our chart. It takes the column 1 and 3, and also it takes the row 1 and 2. So in order for the chart to take this place, we need to assign the CSS properties, and it's going to be the grid column. And we can say it spans from 1 to 3, and grid row is going to span from 1 to 2. So, and this is it. Now we have our chart, which is scaled, and if we want to scale it even more like that, then we'll just reassign this grid column and grid row properties back to the new setup. So this is why it's called the sandwich design, because we use the three layers: the grid container layer, which basically contains all our cells, the cell grid that listens to the events, and then we use the cells to determine the position of the chart, and then the chart layer, which is essentially the main content layer where we place all our financial data. All right, I think this is it for the canvas design. We can now jump into the data store design. So let's create a new section here. So let's call this section data and property model. And before we define the data property model, I think it's good to understand how our hierarchy of the components will look like. So I know that usually it's quite optional to draw the hierarchy, but here the hierarchy will directly respond to the data structure that we have. So I think one of the most useful interface that we're gonna implement is the draggable. So we want to have the generic draggable container that we can wrap any component type that we want to place on a dashboard. So this essentially this draggable interface will implement every logic of the drag and drop. So it will handle the placing on the grid. And it will not have any other logic except the drag and drop. This will allow us to encapsulate this complex part in a single component. So another thing that we want to add is the dashboard component. So what is that? So the dashboard component will be responsible for handling all the data API requests and will fetch the data. So remember we mentioned that all the data will follow the same unified format. This will allow us actually to have the single component that will fetch all the data and pass it to the required chart. So yeah, and this component will be responsible for requesting this data. And you may ask, okay, now we have the draggable and the dashboard element. Where do we have the chart? So the next thing will be our chart element. And it's not really, it's not super complex interface. So our chart element will have just a single property. So remember I told you that each chart model may have a different set of properties. So it's not really following the API format that we use. So it should know how to transform the data that comes from API into the data that is required to render this chart. So, and the way it's going to work is that we define the chart element interface, and this interface will tell us how to transform the data. So I'm gonna use the TypeScript notation. So it's gonna be T chart element, and T will be responsible for the type of data that we're trying to render. So 1 second. Okay, here we go. And I'll call it transformer. You can name it however you like, but for me, it's just something that transforms the source data. And for the source data, I will use the T data annotation to the chart data, which is T. And every chart will implement this interface now. So, for instance, we could have potentially data table. Then we could have pie chart. And essentially, all these charts will have each will implement a transformer, and they will take the data from source. And the source is essentially the data of the same format. So that's why we can use this type of the architecture where each chart implements a transformer. All right, so we defined the transformer interface, and now I think it's time to define the how the data actually will look like. So I think because we're limited, so we'll need to try to limit our data to reflect the system design. So if we add too many parameters, it's going to be very hard to and complex to design this. But because we mentioned that we work with finance data, so this means that our data interface could look like this. So I'll define the type tdata. And let me increase the size so you can see it. Okay, so what do we need for the finance data? I think the first thing that we actually need is the asset. So this can be the stock name on the which is traded on the market, and this will be the string. And then we need a start with a number, and we also need an end. So the start and end is essentially the start of the timestamp of the start point and the timestamp of the end point. It's from which period we fetch the data. So, for instance, we can fetch the data for the last month. So we use the start and then the endpoint to tell the backend which time frame we are interested in. So another important thing is interval. So essentially, in finance data, the interval corresponds to. So when you see the chart on the map, and I can open this trading view again. So the single point, so here we set the chart is 1 hour. So this means that the single point on the chart corresponds to 1 hour. So for instance, this can be 10 o'clock, then we have another candle that corresponds to 11 o'clock, then 12, and so on. So the less the time frame, the more granular is the data, the more data actually we have. If you open the minutes frame, then obviously we could there are a lot of points, and the price fluctuation is not that big. So you can see that the price is more or less stable here, but we have more points. But if we open the 12 months data, then every point will correspond to the single year in this case. Okay, so I hope you understood the idea. And another thing which we need is the points. So what do we display on the chart? And it will have a very simple interface. So essentially we need an opening price and the closing price. So because usually on the charts, we display the data in the candles, where the candle start point is the open price and the candle end point is the close price. So let's do the quick alignment here, and it will be in array. So this is our data interface. And now, so since we defined the data interface, we now need to define the dashboard component interface. So let's copy over and define the T dashboard component. And each dashboard component will take, we need to define what each dashboard component will take as the data. So I think we essentially, what we need to display is the range. So first of all, it's the start and end point. So from which point we display the data and where we end the data. So this will be the range, and it's essentially follow the same format as the T data. So it will be start and end. Then we have the asset, which is string. Then we have the component. And here we provide the T chart union. And essentially this chart union is the set of supported charts. So it can be pie, it can be line chart, and so on. And then we have the method called render. So we take this source with the t data that we have, and then we're supposed to return the component. So for instance, you can provide the component and you can provide the type of chart, but what if you want to have the custom implementation of this render method? So you can take the source and then render any stuff that you want. Another important thing is that usually on dashboard component, we can select the interval. That's why we also need to provide. So it's very similar to the t data here. But here we're kind of mixing up a bit with the state, because each dashboard component can have the state with the range, interval, and the asset. So because the dashboard component will control the request that we send to the backend. So here, let's draw the line to say that this is actually responsible to the for this type of data, and our dashboard component will use the t data. All right, so I think we have the data and property model now, and our next step is to define how do we store this data. So let's save some space here, so we can move this section a bit here, and then let's define the data state. So when it comes to the data storage, we need to think about two things. How do we store the runtime data, so the data that is stored in a global state, and how do we optimize the large set of data and store it on disk, on a hard drive, so we don't utilize too much of the RAM. So, and yeah, here we have two options. So we can store the data in a global state, or we can store the data in IndexedDB. So why IndexedDB? So when it comes to IndexedDB, so this is the only way in the browser where we can store a large set of data on a hard drive. So essentially, each Chrome browser or any other browsers, they utilize around 30% of the, so they allow up to 30% of the hard drive to be stored in the IndexedDB. There is a specific limitation for a domain, so I think it's around 2 gigabytes per domain. So, but anyway, 2 gigabytes, it's quite a lot of storage that we can utilize. So what happens here is we need to think about the data structure, which will allow us to easily access the certain points, so data points for the asset. And the only way to do it efficiently is actually to have the flattened ID structure. So we can write the type, the application state, and this application state will be the following. We can have the key, so let's call it asset ID. So the key of our object will be the asset ID, and it should give us some data structure that will contain the points. But now there is a problem here. So we know that we can have a lot of points. So let's say some key, and then it should give us open number, close number, and it's going to be array. So we need to think about the key that we could build that would work with the multiple timeframes. So remember, we can fetch the data in the different timeframes. It could be 1 hour points, it can be 5 minutes point, it could be second points, and somehow we need to optimize the storage in order to get this data. So for instance, if we have the 5 minutes time frame, so this is our 5 minutes time frame, and we want to fetch the data for 60 minutes, we cannot just essentially store each point which will correspond to 1 second, because if 1 point is 1 second, then if you work with IndexedDB, then just a normal cursor fetch is basically big of n. So this means that within the 60 minutes time frame, if we assume that every minute we have, every second we have a point, we can have around 3,600 points, which is not very efficient because we will need to traverse all 3,600 points. So what can we do about this? One thing, how can we fix this problem, is kind of introduce the buckets. So we can store our points as 5 minutes buckets. So within this 5-minute bucket, we will have at max 300 points. So this 5 minutes will have 300 points. Another will have another 300 points. And you see, within the 60 minutes time frame, we could have 12 buckets. So, and instead of actually fetching all this, instead of fetching, scanning all the 300, 600 points, what we could do, we can scan for 12 buckets, and it's going to be much faster fetch from the IndexedDB and from the runtime. So this is called the bucketing, and IndexedDB is very well optimized for such storage because IndexedDB supports the compound key. So, and this technique will allow us to actually optimize for any time frame. So we can place our points as a 5 minutes bucket. Then we can also have in the same storage to keep the 60 minutes bucket. So if we want to fetch the data for the whole day, then we just need a 24 60 minutes buckets. And if we need to fetch the data for the whole year, we can do the 365 one-day buckets. And essentially, we are only limited by the IndexedDB storage. So there is some overhead on the storage, but remember that the storage itself is not a very big concern, because if we utilize the IndexedDB, it's very easy for us to fetch this data and put it on a hard drive. Okay, so since we introduced the bucket concept, let's understand how can we build the compound key in order to enable this bucketing. Oh, let me check the recording, and yep, that works. So let's remove that. So I guess the compound key should contain basically the index parts that we need for the fetching, and the first index part should be the asset ID. So it can be, for instance, Apple. The next key we need to introduce is the bucket ID. So essentially, we can have a multiple. So each in our storage, we have the multiple 5 minutes buckets, and we need to somehow have an ID for each of them. So let's say this will be 0, then the second one will be 1, and the third one will be 2. And I'll explain how do we calculate this just in a second. And next important point is the time frame. So remember we talked about that we can have a multiple buckets. So it can be 5 minutes bucket, it can be 60 minutes bucket, and so on. So that's why we call it time frame. And this will be the compound key that will contain 3 parts. So asset ID, and then the bucket. And all of this will lead to our T data array, so with all our points. So let's have a good color for that. Okay, and now let's define the bucket. So the bucket, the time frame of the bucket could be 5 minutes. It can be 1 hour. And it can also be 1 day. And they're not really intersecting because we can utilize all of them and store our points in the sense in the multiple buckets. Yes, there will be overhead on the storage, but as long as it's on a disk drive, we are not really putting this in the runtime, so it doesn't really overhead our application at this moment. So the next thing that we need to understand, how do we calculate calculate the bucket ID? So for instance, if we have the current time, which is equals to 0, so let's assume that the timestamp that JavaScript give us is a 0. So our bucket ID will start as 0. Then if we take the 5 minutes time frame, then within the 5 minutes we can have 300,000 milliseconds, and the time from 0 to 300 milliseconds will correspond to the bucket 0. And if we need to put the data in the bucket 1, then the data will start from the 300,001, and the bucket ID will be 1. And you can guess the formula here. So essentially the formula for the bucket ID will be equal to bucket ID equals to our bucket time frame divided by the current time. Oh, actually, sorry, it's current time divided by the bucket time frame. So in this case, since we have our bucket is 300,000, we need to divide 301 by 300,000 and get the remainder of our division, which will be 1. So that's why it's bucket ID 1. Okay, you may now ask, we actually need a lot of storage in this case. And yeah, you might be right. But the best way to understand how much storage we need is actually to try calculating this storage requirement. So we can introduce a new section called storage requirement. And let's try to calculate how much storage we'll need to store the data. So the first thing that we are keeping in our storage is the asset ID, because we use it as a key. And because our asset ID is string, and we know that one symbol within the string takes 1 byte, we can assume worst case where the asset ID is 8 bytes, 8 symbols. Another thing is the start. Oh, not actually the start. So, and also we keeping our points in the open and close format. So we keep the open price and the close price. So open is 4 bytes, then close as well as 4 bytes. So the one point entry will be 8 bytes. The next thing is the bucket ID that we're calculating. Because it's a number, it's also 4 bytes. That's okay. And also the time frame. So the time frame can be expressed either as a character or the string. So we can say we can express it as a character, and the maximum character that we can have is basically 2 chars, and this will equal to 2 bytes. Okay, so, and let's avoid, because IndexedDB itself is the object storage, so it actually stores the objects. We can technically kind of amend how much it takes to store the object thing and use these parameters to calculate the data. Okay, so how much data can we store in the worst case for the whole day, assuming that we have the 5 minutes time frame? So this can be calculated as the following. So let's open the calculator. So to calculate the number of points that we can store per day, we can assume that 1 second at max will represent 1 point. So the worst case scenario is in every second of the day, we get 1 point of the data. So if we take 24 hours, multiply by 60 minutes, so we get 440 minutes. Then we multiply it by 60, so we get 84,400 points in total. So these are the maximum amount of points, assuming that we get every second every second of the data. So, and we can put this data inside our estimates. So if we have 800, 400, 1 sec, I'll check the number. Yes, 86,400 points. So we need to multiply by the size. So we know that our single point will contain 4 bytes of the for open and closed data, so it's 8 bytes. And we need to multiply this number now. So let's go back to calculator. So we multiplied by 8. So, and we get, 691,200 bytes. So let's try to convert this number in megabytes now. So this will be, 1 second. We actually calculate bytes and megabytes. So it will be 0.7 megabyte per asset for the whole day. So now let's go back. So 0.7 megabyte of the data for 1 day. And if we want to estimate how much it will take to store the data for the whole year, then we need to multiply this 0.7 multiply by 365, and let's calculate it as well. So 0.7 multiplied by 365, so we get 255 megabyte of the data. So this is 255 megabyte. So that's how much we need to store the data for the whole year, for the whole second. And this is the worst case scenario. And how do you think we will actually reach this limit when we work with the data? So do we actually fetch every second of the data for the whole year? Because it's an upper bound, I wouldn't worry so much of the space. Generally speaking, when you look at the financial charts, you actually don't select the second time frame. You usually select the 1 hour time frame, and so on. And what do you think will be the number of buckets here? If you want to determine the number of buckets in the day, then we need to do another calculation. So we can see, we know that in a day, we can have maximum of 1,440 minutes. And if we split it by 5-minute buckets, we get 288 buckets if we store it as a 5-minute time frame. So let's set it, 280 buckets if for 5 minutes time frame, and one single bucket will contain the amount of, let's divide the total number of points. So let's put it here like that. So in total, we can have around 338 points per bucket. That's the maximum amount, 380 buckets. That's it. So this is how we calculate the storage requirement. And of course, if we increase the bucket size, so for instance, we can have the 1 hour time frame or 1 day time frame. This means that single bucket will contain more points. So storage wise is going to be the same, but the number of buckets will really reduced. We can actually store all of these time frames. And if, for instance, if we're trying to display the chart for the whole year, it's more optimal to use the 1 day time frame. If we're trying to use the monthly chart or daily chart, it's obviously we can utilize the hour time frame or 5 minutes buckets. So essentially, it all boils down to the space that we have. And one thing that we can do for the global storage, so is to reduce the durability of the IndexedDB. So if we reduce the durability of IndexedDB, it will allow the IndexedDB to increase the throughput that we can, basically the number of requests that the IndexedDB can handle. And in terms of financial data, it's not very super critical to reduce the durability, because we don't need all the data to display the chart. So to display the chart, we just need a part of the data. So that's why also the reduced durability, if we even lose 1% of the data that we commit for the transaction, it's not that critical for us. Okay, so the next concept that we need to touch base upon is data upsampling and downsampling. So for instance, what if we have, so imagine that we work with a 5 minutes time frame. So we have multiple buckets. This is bucket 1, then we have bucket 2, and then bucket 3. And here we have a kind of timeline. So we start at 0, and we end at 60 minutes. So, and you can assume that we have more buckets here. Just I'm not drawing all the buckets to make it simple. What if we want to change our time frame of the displayed data, for instance, to 1 hour? So at the moment, it's 5 minutes. So this means, can we somehow to downsample our data? And we have a lot of data. So essentially, we need to convert our granular data to less granular, less accurate data to the 1 hour time frame. So this, can we have a single 1 hour point? And the answer is yes. So we don't really need to request a new data from the server, assuming that we have all these buckets available to us already. So the way it's going to work is we can take the bucket, the first bucket of the data, to use it for the, and remember, our point contains open price within the time frame and the close price. So we need to take the first point of the first bucket to get the open price, and then we can get the the close point from the last bucket within this time frame and get the close point. And then this will convert to a single 1 hour point. So this is called data downsampling. And this process is usually lossless. This means that we're not actually losing any data because we're converting from more data to the single point. And this is very useful in order to reduce the number of requests to the server. So if we have all the data is inside the IndexedDB, so we can actually downsample the data to the wider time frame and save some network requests. But what if there is in the opposite situation? What if we have a 1 hour frame and we need to upsample the data in order to display it as a 5 minutes time frame? Here it's a bit more interesting because you can't really go from less accurate to more accurate data without the server request. So, and the only way how can you actually do that is to use a placeholder data. So for when we do the upsample, this means that we actually need a server data. So we want to fetch the new data to display for the user. But while the request travels to the server, what we can do, we can essentially create the empty buckets, and every bucket will contain just one entry. And this will be a duplicate entry of the 1 hour entry. So we are doing this just to not display nothing on the chart. It will be the placeholder. So our chart will still be loading, but at least we display something. And comparing to that, where we have 338 points here. So this is just acts as a placeholder. So data upsample is a loss in terms of the data. It's more like a temporary solution for us to display something before new data arrives. Yeah, that's the downsampling and upsampling. So just the key thing to remember: when you do the downsample, you can reuse the data to create a less accurate point, while when you try to upsample, you need more data. And in order to initiate more, to extract more data, you either need to have some metadata from other buckets, or you need to request the server to get more data. All right, so I think we covered the data storage now. So the next step will be so what's in our plan? Yes, to talk about the API. So now let's think about the API and what we can do to unify our network requests. So I'll create a section called Data API. All right. So first of all, we need to remember we discussed that our data API may have lots of like legacy APIs. So we can assume that we have multiple endpoints using different technologies. So we kind of want them to unify under a single interface. And for that, I'm going to introduce the get data interface, and it will take the asset ID as a first parameter. Then we take the start point, the end point, basically the time frame, and time frame, which is can be 5 minutes, can be 1 hour, and etc. And our data interface will return our data format, which is tdata. All right, so now we kind of want to unify all our endpoints under a single interface. And I'm proposed to use the subscription interface because essentially we need to subscribe for a certain data and then receive it. And this subscription interface can implement different stacks, like we can do the short polling, we can do the HTTP streaming, we can do server-side events, and so on. So in terms of the technology-wise, what we can utilize is the first and the most common thing that is used on the trading applications, the WebSockets. Another technology that we can utilize is the server-side events. The third technology is HTTP streaming. Why not? And the most trendy one that should replace many things soon is web transport. And let's talk about each of them in pros and cons, and try to decide which technology we would use for our API layer. So when it comes to the WebSockets, what are the pros of the WebSockets? I think the first and the most important one is real-time communication. So this means that we have a very low latency, we get data very fast, and that's quite important in trading apps. So this is definitely a pro. But what about the another pros? So the WebSockets, they transfer the binary data. And I'll explain why transferring the binary data is important for the financial apps just in a second. So the next thing is the dual communication. So you can send the data to the server and and to the client. But what are the cons of the WebSockets? And in terms of the cons, we have the hard, like, edge complexity in terms of the implementation, because you need to work on data serialization, then error handling, reconnection, and state handling. So the issue with the WebSockets, it's since they are stateful, this means that if we lose the connection, we need to restore these connections and how to restore the state. And you usually maintain the separate infrastructure to maintain the WebSocket states. And it's also very hard to scale in terms of infrastructure. There are many issues with that. So I do think that WebSockets, at some way, they will be replaced soon, although they do provide a very good real-time performance that sometimes is needed for the applications. So for servers and events, the cool thing about servers and events, they are HTTP2 based. They are stateless. So this means that if, for instance, 2 nodes failed, the HTTP protocol will handle the reconnection and error handling. So reconnection and error handling comes out of the box. And also because it's HTTP2 based, it's we can use the multiplexing. So the cool thing about the multiplexing is one single TCP connection allows us to split the connection into around 200 streams based on depends on the browser. So we can fetch 200 stocks in parallel using the one single TCP connection for the multiplexing feature, and it's pretty cool. In terms of the code, okay, one more pro is it's easy to scale and use. So one of the cons of the server-side events, it's still slower than WebSockets. It's still it's text data, and I'll explain what's the comparison between text data and the binary data just in a few seconds. So, and it's also single communication. I would say mono-channel, because you can only send the data from the server. In our case, it's not actually a very big con because we're just in the financial dashboard, we usually just read the data. But for some apps where you need to have the real-time input to the server, that's important. Okay, so the next thing is HTTP streaming. So when it comes to HTTP streaming, the pro is we still stream the binary data, and it's benefits from all the HTTP2 features. But the con on HTTP streaming is usually it's pretty slow, because there is an issue that TCP stack requires the handshake, reconnections, and usually it may impact significantly the latency. Also, the HTTP streaming doesn't support the envelope marking. So I know that there is an official term for that, but I forgot. So essentially, envelope marking means the following. So imagine that you fetch the points. Your points are marked like 0 to 100. So this is the time frame. 0 to 100 milliseconds, then you have 100 and 200 milliseconds. So when you can mark the envelope, you essentially can build the frames of data. So this is the first frame, this is the second frame. So this is not supporting as a part of HTTP streaming. So, and because we cannot mark properly the data, it's not super useful for the financial data because we need to mark the frames. And usually HTTP streaming is more like for files where you don't really care about how you mark this frames. So let's say the con is no frame marking. So it doesn't really suit us in this case. So the next thing is quite cool, which is the web transport. So the thing with the web transport, like back in like 5 years ago when we spoke about the HTTP2, so this HTTP2 had the same limited support as the web transport now, but now HTTP2 is the de facto standard. So the web transport is supported by 60% of the browser and not all the servers, but the pros of the web transport is it's UDP based, and it's like not actually it's UDP based, but it's also QUIC based. And the benefits of the UDP and QUIC is because it's not a TCP stack. So this means that the messages can be transferred to the client without the reconnection. So this is called zero RTT. So essentially, the web transport doesn't require the freeway handshake that is required for the TCP stack, and it saves a lot on latency. So it's actually faster than WebSockets. And because it's faster, so this actually can help us replace the WebSockets in the future. So, but what are the cons? The cons is, limited browser and server support. There is also one more benefit. It still transfers the binary data, and it supports data framing. Okay, well, definitely for modern apps where we have no browser limitation and we can use the modern servers, the web transport is the best option that we can utilize. So, okay, now we describe all the benefits. One thing that we mentioned here is the comparison between the text data and the binary data. And the main thing about the binary data, so when the data is represented in a binary format, it's very easy to compress. So we can introduce any serialization technique, any serialization protocol. So one of the popular one is the protobuf, but you can place any serialization protocol and it will work the same way. So the protobuf can allow us to compress the binary data with a 6-8 times efficiency. So this will allow reduce the data blueprint and significantly improve the latency. And when it comes to serialization and deserialization, there is a price that we pay on deserializing and serializing the data. But I think in terms of when it comes to transferring a large amount of data, introducing deserialization is not a bad thing. So we can actually use it and significantly reduce the size of the data if we want that. This is an optional, and if we can do it if we want it. So the next thing is CDN to ensure that we actually have the low latency across the regions. And yeah, that's our server. So I'm not going to design the protobuf schema for the data, I think, because I think it's just too much for the system design interview. So now our data API stack is complete, and I think we can briefly touch on one of the interesting concept, which is the multi-window support. When it comes to multi-window support, there is an important concept that is always used. So first of all, what is the multi-window support? Essentially, we have the window 1, and it acts as a host. So it's essentially a main window that handles all the event changes and the state changes, fetches the data, and so on. And this window has its own state. And what if we, for instance, like I'm a trader, I want to open another tab and then move this tab to the second monitor, and I want this monitor to be an extension of my application. So it shouldn't be a standalone application. It should act as an extension of this application. And if we want to do that, so we need to create the second window, and we'll call it extension. And this window itself will have its own state. But there is a big difference here. So let's also create a section on our system design. So let's call it multi-window support. So somehow we need to establish the communication layer between the window 1 and Windows 2. And somehow the window 2 needs to understand that it's an extension. So, and essentially the host will control all the layout and the sync configuration between the window 1 and window 2. It will also write updates to the state. So we don't actually want window 1 and window 2 to write the states, both state updates. So the state from the window 2 will be actually a replication of the window 1, and the window 1 will be the main controller of the state. So we can put this quick note about that. So the host will control the layout and the sync configuration. It will also write all the updates. So, and one of these way how can window 1 understand that it's a host and window 2 as an extension is the local storage. So the local storage is shared between all these tabs because we run the same window. So essentially, because we run the window 1 and window 2 on the same domain, the local storage is the same. So the window 1 will write the data to the local storage, while the window 2 will read this data. And let's call it local storage. And what do we actually need to understand that we have a host running? So we'll create a variable called host ID, and it will essentially contain the window ID. So if the host ID is not null, this means that when the window 2 is open, then we have the host that we need to connect to. So, and we can also create an extensions ID. So assuming that we may have multiple extensions. So this is extension and then a window ID array. So whenever the second tab is initialized, we will put the extension ID inside this extension array. So that's how we store the data. So it's a relatively simple storage. So we don't really need much because we're not utilizing local storage as a global state. This is just basically needed to establish the communication. So, and the thing is, how do we like synchronize the state? How do we keep the communication channel between window 1 and window 2? So there is a default API which is provided by the browser called broadcast channel. And essentially it allows us to send messages with the payload from window 2 to window 1 and backwards. So we could potentially have the following structure. So we can have, for instance, event called chart, then the asset ID, and then the source ID. And we can actually structure it even better. So for instance, we can have chart and then say payload. And this payload can be arbitrary, of course. So, and for instance, this event will tell us to fetch the data for the chart 1. And then the window 1 can fetch this data and put it in the state where the window 2 can can read this data. I know it's very high level right now, but we don't really need to dive into the super details how we implement this. The main concept here is that we are implementing the broadcast channel, and the event system between window 1 and window 2 is very customizable. We can use the Redux-like patterns here to make sure that the state is correctly updated. So the main thing to know about the extension, it doesn't modify, it's so we can add more charts, but we don't really modify the states directly. We always read from the same IndexedDB. We'll also read from the local storage, but we don't write. So we tell the window 1 to write the data and fetch the data. So this way we can avoid the race conditioning where we have multiple windows, each writes the data, so we don't need to really worry about the synchronization of the data. So it's more like a simple approach in this case. So, alright, I know that this system design took a while, and I hope you really liked this video. So we uncovered pretty much quite a lot of interesting details about the APIs, how to do the sandwich design, how to implement a drag and drop. So I will be very happy if you put the comment on this video, hit the like button, subscribe to the channel. This is the best way to support my effort. And yeah, I have a dream to reach 100,000 subscribers to get a YouTube button. So you can get me closer to my goal by subscribing to the channel. And see you in the next videos. I hope that it will not take me 2 years again to publish another one. See you guys. Bye.